What's that?
I think I got you.
Okay. So this is what I get when I simplify it. I get 1/2 the natural log of x squared plus 1 from this term, just the natural log of x minus 1, and then subtract the one that's in the denominator. Take the exponent out. Okay. Then use implicit differentiation here, and just normal differentiation. This one you'll have to use the chain rule. Theoretically, you use the chain rule here, but it's trivial, so because it doesn't have. If it had a constant in front, you'd have to worry about it. Or if it had a power, but if it's just x plus or minus some constant, it's just 1 over that argument.
I haven't simplified it yet.
Oh, okay. That's good. I think she's got it. Okay. So you guys marching in the parade on Friday? The Clifton Forge parade? Oh, is it Saturday? Well, Friday. Covington's Saturday. Clifton Forge is Friday, right? Yep. Okay, so there's the answer. So the chain rule says you multiply this by, it's 1 over this times the derivative of this, 1 over this times the derivative of that, which is 1, and then minus 2 times 1 over that. And then you multiply by y. I substituted y back in. So the way you'd simplify this is you would have to find a common denominator. So basically, you would this term in the brackets. You take this term and multiply by those two terms, and then you take the second term, 1, and you multiply by the other two denominators. And finally, I'm running out of space here, is you would have minus 2 times the product of those two things. So I'm not sure how I'm going to do this because I run out of space. Let me put it on one page and shrink it up a little bit. Oh, that's not what I want to do. There we go. Like that. So you'll leave. What we'll do later on is we'll simplify those with these. We're not going to multiply out the denominator. We'll just combine these with the appropriate ones over there, and then we'll have that as our coefficient, whatever the heck that is. So go ahead and figure out what that is. So that's x times x minus 1 times x plus 2 plus 1 times x squared plus 1 times x plus 2 minus 2 times x squared plus 1 times x minus 1. So I'm not going to do it yet. You're going to have to try to. That's usually why I don't ask you to simplify it, especially on a test, because you could spend 10 minutes simplifying it. So what I was doing here, I was just multiplying this out, and then I was going to multiply it by x to get the first term. These are pretty easy because you can just use FOIL on them because it's just two terms. Oh, by the way, does anybody like candy corn? Just Xavier. So if anybody wants them, go see. Yeah, but I don't like candy corn. Martha used it to make her little turkey head for Thanksgiving. So she only needed one candy corn. We had to buy a whole bag of candy corn. Anybody get my answer? Yeah? Okay. Margaret, Evan. I trust you guys. The interesting thing, it's interesting just looking at the original function because you got the square root of x squared plus 1 in the numerator. When you take the derivative of that by itself, you'd end up with you'd have x squared plus 1 to the 1/2 power. So it's not surprising that the result has x squared plus 1 to the minus 1/2 power. So that makes sense. Typically, when you have something in the denominator that's raised to a power, the power gets increased by 1. So if you had, for example, 1 over x squared, when you take the derivative, you'd get negative 2 over x cubed. So that's also not surprising. The thing that made me ponder whether I made a mistake was that the x minus 1s actually just canceled out because that didn't end up being a term. And I guess that's just the way it is. That's just the way it is. Okay. On to the next problem. This next one's easy. So the integral of e to the negative 3x dx. So you're just going to use u substitution where u is equal to negative 3x. Yeah, don't forget your dx. Yeah, it's easy to forget that dx when you take the derivative of u. So your answer is negative 1/3 e to the minus 3x plus c. Now I'm just going to set up a little table here. So this is f of x, and we're going to have 3 columns. F of x, f prime of x, the integral of f of x dx. Okay, so these are all just e to the something x, minus x, 4x, negative x, 7x. So when you take the derivatives, all you ever have is you just take the coefficient in front of the x and multiply the original function by that. So if we had the derivative of e to the 4x, it's just going to be 4e to the 4x. And if we had the integral of the derivative of e to the minus x, it's going to be minus 1 times e to the minus x. And the derivative of e to the 7x, just 7e to the 7x. So since this is so easy, you really shouldn't have to resort to using u substitution after you get used to it. So again, when you take the derivative, and it's like with the sine function, the sine of x is going to be 7 times the cosine of x. Here it's even simpler because you don't even change the function. You definitely don't change the argument because we never change the argument. So all we have to do is add this constant in front of it when we take the derivative, whatever this constant is. The only one this is probably the hardest one because you don't see negative 1, so you might not as easily decide that. And the same thing applies for when you take the derivative, except you divide by whatever that constant is. So if you integrate e to the negative 2x, it's going to be negative 1 over 2 e to the negative 2x plus c. Here you get 1/4 e to the 4x plus c. Here you would get negative 1 e to the, negative 1 over 1, which is still negative 1, to the negative x plus c. And this would be 1/7 e to the 7x plus c. So you just divide, when you integrate a reasonably simple form of the exponential function, you just divide by the constant that's multiplied by the x in the exponent. So if you're doing derivatives and you have a product rule and part of the product involves e to the 7x, you don't have to go to the whole trouble of saying this is f of u. You just say, oh yeah, I remember you said just multiply by the constant. Because what we have, this is, f of u is this. So the derivative of f of u is going to be when it's e to the u, the derivative is e to the u, and you multiply by u prime of x, which is always going to be just the constant remaining if you don't have any powers on the x values. Okay, and the last one is this one. So it's using u substitution. The exponent is going to be u. But remember, because it's a definite integral, we're going to change the limits. So we're going to redefine the limits in terms of u, just like we normally do. So you'll have u equals x cubed, and somewhere down you'll say when x equals 1, u equals something, and when x equals 3, u equals something. Using our definition for u, or not our definition, our choice. Don't forget dx.
Oh, yeah.
I'm the dx police here.
Remember this time.
Did you remember this time? Okay. That sounds like a rap group. The DX Police. Yeah, so I'm going to be just as picky as I was last time as far as when the test is concerned. So be careful about little things like forgetting your dx or leaving the integral sign on when you shouldn't have. You should have taken it off. There was something earlier that I was like here. Notice I put the parentheses when I have a negative sign in front of this du part. I put the parentheses to make sure that I know that I'm multiplying it instead of subtracting it. What else did I have here that's you got to be careful about? I guess that's about it so far. Yeah. Oh, you're right. I can't. Thank you. It's a big number. E to the 27th power. Wow. What is it? Does it even work on a calculator? That's a heck of a big number. 5.32 times 10 to the 11th. plus E. I'm not even going to worry about that. Divided by 3. Yeah, it's surprising how big that, you look at that function, it's only between 1 and 3, and the area underneath that curve is 1.77 times 10 to the 11th. Wow. Interesting. Okay, so that's it for that. You guys can turn that in later. Oh, that reminds me, I've still got a few papers that I always forget to hand these back to the non-physics people. Pretty much Evan and Tessa and Daniel. Okay, so last time we talked about we came up with the integration formulas and derivative formulas for situations where the base was something other than e, so something other than the natural logarithm. We're going to, so I've forgotten where I've stopped assigning homework. I need to assign some homework here. So let me open this up. So what's the last section I assigned homework from? So I haven't done 5, 5 yet then. Okay, so 5, 5 I think is bases other than E. So I'll just give you some homework problems to do with that. So it's not that many. It's basically just like dealing with natural logarithms and natural exponentials, except you've got to have that extra 1 over, the natural log of the base, either divide or multiply by. The next section is actually the last section that we're going to cover in this semester. But it can get fairly interesting. So we're going to spend, it'll take, what is today? Friday, Thursday, Friday, Monday, Tuesday, yeah. We'll need all of that time. Actually, I'm just going to, section 6 is associated with inverse trig functions. So this is chapter 5, section 6. So what we'll learn how to do is how to take the derivative of the inverse trig functions and what the argument in the integral has to be to get the result. The integral is the inverse trig function. It's kind of like the logarithm. The derivative of the logarithm is 1 over x, and the integral of 1 over x is the logarithm. In this case, we're not going to go the way we did with logarithms. We're going to start with the function and figure out what the derivative is, and then knowing the derivative rule, we know the integral rule. But let's kind of do a little review on inverse trig functions. Actually, I'm going to pull up my notes because I got some drawings here, so instead of winging it. Okay, so if you have a right triangle, in this case it's a isosceles right triangle because it has two sides of the same length. And we know that if each side is 1 unit, that the Pythagorean theorem is going to give the hypotenuse to be equal to the square root of 2. So given that configuration, the question is, what is the angle? So what we would do is we use the inverse trig functions to kind of pose that question. So we could ask that question 3 different ways, in terms of what is the angle. We might say, what angle has a sine value of 1 divided by the square root of 2, question mark. We might say, what angle has a cosine value of 1 divided by the square root of 2, question mark. Or what angle has a tangent value of 1 divided by 1, question mark. So what I've done there is I've just used the definition of the sine, the cosine, and the tangent with the dimensions of the right triangle to pose that question. And I took the opposites for the sine. I took the length of the opposite side and divided it by the length of the hypotenuse. And I said, what what angle, there's only, with this particular ratio of this length to that length, there's only one angle that results in that. One angle as far as between 0 and 90 degrees. And then same thing with cosine. I said, well, the definition of cosine is 1, the adjacent over the hypotenuse. So, what angle has a cosine value of that? Or with looking at the opposite over the adjacent, that's the definition of the tangent. What angle has a tangent value of 1? And the way we kind of symbolically represent that question is we would say, so this one, we would say theta equals either the arc tangent sorry, wrong function here. Arc sine of 1 divided by the square root of 2. Here we'd say theta equals the arc cosine of 1 divided by the square root of 2. And theta is equal to the arc tangent of 1. There's two ways of doing it. You can say the arc sine, or you can say the inverse sine. So they mean the same thing. I guess you can use them interchangeably. So you might read this as theta equals the arc sine of 1 over the square root of 2, but you could also read that as what angle theta has a sine whose value equals 1 divided by the square root of 2. It's kind of like with logarithms. When you think about logarithms, you're asking what power do I need to raise a base to get the argument of the log function. There's some other things about, what we can say is that the sine and arc sine are inverse functions. So what that means is that the sine of the arc sine of x equals x, and the arc sine of the sine of x equals x. So the sine of the angle whose sine is x is x. And you can do that with you can do that with the other functions. So the same for the cosine and arc cosine and tangent and arc tangent. That's how we use these properties to be able to solve trigonometric equations in pre-calculus. One other thing about, but if you, let's go to my graphing program here. If I plot the sine of x, looks like that. So one of the requirements, there's a couple of requirements that I didn't mention earlier that I now remember. There's, for two functions for a function to have an inverse, there are a couple of requirements. One is that the function, well, first it has to be a function, and secondly, the function has to be one-to-one. Does anybody remember what one-to-one, a one-to-one function means? Because a function means that for each value of x, there's only one value of y, and we use a certain test to tell whether something was a function. Remember what that was called? Yeah, vertical line test. So you can tell this is a This is a function, but a one-to-one function says that for each value of x, there's one value of y, and for each value of y, there's one value of x. In this case, the sine function is not a one-to-one function, because for a given value of y like this, I can get I actually have an infinite number of values of x, which have, say, a y value of a half. So it's not one-to-one, and that's one of the requirements for an inverse function. Inverse functions have to be one-to-one. So let me just, the most important one that we know is e to the x and the natural logarithm of x. So if I plot those, so let's say e is the function and the natural log is the inverse. You'll notice that for every value of x, there's one value of y, so it's a function. But for each value of y, there's only one value of x. It's what we would call monotonically increasing. It just means it continues to increase. It doesn't go through any loops, bumps up and down. So both the blue curve and the red curve are one-to-one functions, but the sine isn't, because it goes up and down and up and down and up and down. So it's not one-to-one. So what we do when it comes to inverse trig functions, we limit the domain of the trig function so that it is one-to-one within that domain. So let's go back to the sine function here. So if I graph that, and let me just take a picture, stick it in my notebook here. And we arbitrarily decide that we're going to limit the domain of the sine function from here to here. So what we do is we say that x is going to be between negative pi over 2 and positive pi over 2. That makes the most sense because we want it around zeros. Having it near to 0 makes the most sense instead of making it around x equals 5,000. So, and then if you look at 0, if I chose from 0 to pi, it wouldn't be one-to-one because it has that hump. So for one value of y, there'd be two values of x. But if I choose it between negative pi over 2 and positive pi over 2, I'm going to eliminate the rest of the function by just marking it out with this, just scratching it out. So if I scratch this out like that, so I'm not worried about that, and I'm not worried about that. And so now the part that's left over is a one-to-one function. So I could say, let me move this over a little bit. Actually, let me just move that down. Now move that over. So if I said the sine of theta of x, the sine of x with the limited domain, I'll say with domain is 1 to 1. Okay, so now that it's 1 to 1, I can have an inverse function of it. So, and notice the domain here for the sine function is from negative pi over 2 to positive pi over 2. The range is from negative 1 to, we'll say y is equal to positive 1. So that's the range. That's another thing about inverse functions. When you have a function, the domain of the original function is the range of the inverse function, and the range of the function is the domain of the inverse function. So what I can say about the inverse sine, or the arc sine. So I can say, so the inverse sine of theta or x, or whatever you want to call it, has a range of negative pi over 2 to positive pi over 2, and a domain of, and actually I guess I should say y here. The domain is from -1 to +1. And if you plot the inverse sine function, let's plot that on my graph here. So it would be probably arc sine, I think. So that's what it looks like. I need my camera. So you can see the domain here goes from -1 to +1, and the range would go from negative pi over 2 to positive pi over 2. So they get flipped around. So that's what so what does the inverse sine function look like? Looks like that. It doesn't have the domain from -infinity to +infinity that the sine function has. It only goes from the domain only goes from -1 to +1, and the range only goes from negative pi over 2 to positive pi over 2. But it does have slopes, or it has areas underneath curves. So we should be able to figure out a way, we need to figure out a way of finding the slope of this curve, the slope dy dx. And if I wanted to find the area underneath this curve, I want to be able to do that too. So the question is, how do we come up with an equation for the derivative of the inverse sine, inverse cosine, inverse tangent? The inverse cosine is going to look something like this. Let's plot the cosine function first. So if we plot cosine of x, looks something like that. Need to zoom out a little bit. Again, the cosine is not a one-to-one function, so we have to limit the domain of the cosine function so that it is one-to-one in that domain. So what we would do is look for similar values of x where it's one-to-one. And it turns out that if I chose from negative pi over 2 to positive pi over 2, which is from here to here, I'm trying to get it out of the way of this little box. There we go. If I chose the same, if I chose the same domain as I did for the sine function, you'd see that it's not one-to-one at that point. So that's why we choose it from 0 to pi, because from 0 to pi it is one-to-one, and we ignore everything else. So let me add a page to that. So to make the cosine 1-to-1, we limit the domain to 0 to pi. And I guess we include it, really. It should be equal to. And that's why, both of these things, if you use the inverse trig functions on your calculator, if you do the inverse, you're always going to end up with between negative pi over 2 and positive pi over 2. If you use the inverse sine function, if you use the inverse cosine function, you'll always end up with the value between 0 and pi in terms of radians. If you did it in degrees, you'd get between 0 and 180 here, and between negative 90 and positive 90. And it's all because you have to limit the domain of the original function so that it's 1 to 1. So then you know that you can take a you can have an inverse existing. The range is still negative 1 to positive 1. So I guess I said y before. I'm going to put x, sine of x. So if x goes between 0 and pi, the range is between the sine of x is between negative 1 and positive 1. So that says that the range of the inverse cosine or arc cosine of x is 0 to pi, and the domain is negative 1 to positive 1. Okay. So now we're going to derive how you come up with the derivative for the arc sine. And what you do is you do a right triangle. So we're going to have a right triangle. Okay, so that's 90 degrees. We'll call that x. The angle is, well, actually the angle, yeah. Let's say theta. Theta is going to be the arc sine of x. So this is theta. And what we're going to do is we're going to make the length of the opposite side be x. And the length of the hypotenuse 1. And that would, by the Pythagorean theorem, that means that the adjacent side is going to be 1 minus x squared of 1 minus x squared, because a squared plus b squared equals c squared, and if this was the unknown, you could solve for this unknown and you'd get 1 squared minus x squared is equal to this squared, and then you take the square root. And so by defining this as x, the opposite side is x, and the hypotenuse is 1, this has to be 1 minus the square root of 1 minus x squared. Okay, now I'm trying to remember how to. So what you do the same thing. Remember when we looked at the derivative of the exponential function, we used logarithmic differentiation. Well, we're going to do something similar to that here. Just accidentally put my speaker on here. Let me turn that thing on. So we are going to say that, well, one thing is we can say is that the sine of theta is equal to x over 1. So based on how I've defined my triangle, the sine of the angle theta is the length of the opposite side over the hypotenuse. So you can also say that another way of representing that is that the sine of theta equals x, or theta equals the arc sine whose value equals x, in this x over 1 in this case, which is x. So what we're going to do, instead of taking the logarithm both sides, we're going to take the sine of both sides. So we're going to take the original function here. So let's write that back down. So you have this theta equals the arc sine of x. You take the sine of both sides. So you take the sine of theta equals the sine of the arc sine of x. And again, you're going to use the inverse properties here. The inverse properties of the sine and the arcsine. Well, the sine of the arcsine is x. So you get that sine of theta equals x. So that's equivalent to the original expression. Theta equals the arcsine of x. The equivalent expression is the sine of theta equals x. Then you take the derivative of both sides with respect to x. So you'd say the derivative with respect to x of the sine of theta equals the derivative with respect to x of x. It's kind of, again, we had the same kind of thing happen when we looked at the derivative of the exponential function. So here we just get 1. And on the right-hand side, we get the derivative of the sine of theta with respect to x. Well, the derivative of the sine of theta is the cosine of theta. And then you have basically theta prime. So you use implicit differentiation. So you take the derivative of this, theta prime is d theta dx. And what I'm really trying to do here is I'm trying to figure out what theta prime is. I'm trying to figure out what is the derivative of the arcsine. Well, it's the same as the derivative of theta. So what we do is we solve for theta prime, which is what we're trying to find, the derivative, and that's equal to 1 over the cosine of theta. But I want this expression not in terms of theta, but I want it in terms of x, because the original function was in terms of x. So what we did, we did the first problem we did in class today when we used logarithmic differentiation. The last step was to multiply both sides by y and substitute that back in. Well, it's not quite as simple here, but what you can see is that in terms of my original right triangle, if the sine of theta is equal to 1 over x, we can say that the cosine of theta is equal to the length of the adjacent side divided by the hypotenuse. So the cosine of theta, based on my originally defined triangle, is equal to the square root of 1 minus x squared. So I plug that back into my equation. And so I get 1 divided by the square root of 1 minus x squared. So if f of x equals the arc sine of x, f prime of x equals 1 divided by the square root of 1 minus x squared. So that is the derivative, which is also the slope of the tangent line to the curve that we showed earlier, the one that kind of looks like a sine, but it's rotated 90 degrees. And that's kind of cool because, the arc sine it's not an algebraic function. It's a transcendental function, just like exponentials and logarithms. But it turns out that the derivative of the arc sine is actually it's a algebraic expression. And we'll find out for the arc cosine and the arc tangent, they're also algebraic expressions. And that little interesting fact we'll see again in the latter part of the second semester when we talk about infinite series. So I'm going to give you just a 1-minute introduction to infinite series. The sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... Okay. So the sine, which we think of, we just know we get it out of the calculator. But the question is, how does a computer or calculator figure out what the sine of something is or the arc sine of something? They don't have a table that they look at values in. They have to have an equation that the computer can do. And computers can add, multiply, divide, and subtract. So to find the sine of x, we'll find out later that there is an algebraic a polynomial type expression that if you add enough terms together, you'll get, if you add an infinite number of terms together, you'll get the exact value for the sine of x. And that's kind of the same thing we see when we derive the derivative of the arc sine. It ended up being an algebraic expression. So it's not surprising that later on we'll find that you can represent this non-algebraic type expression as an algebraic expression. Okay. So we'll continue on this tomorrow.